In the last video we have designed this the nbit register. Now in this video we're going to design the test bench file, so and then simulate it. So let us create a new Verilog file and save it as nbit register test bench and nbit register, and then save it. So the first thing that we're gonna do here is declare our timescale. So timescale 1 nanosecond, (100 picosecond), and then our module name is test bench nbit register, and then end module. So what we're going to do first is insert our module. So it is this one here. With let me copy all of it. So it is this module here, and then we need to give the names of it. So the first one, so we're gonna test bench D, and then it's test bench clock, and then test bench load, test bench reset, and then test bench Q. So next thing that we're gonna do is to declare those this values here, the input and output. So we have our inputs are reg, so it's reg. First is test bench D, so it's D, and we know that it is have bit length of 3, and then the other input, it is clock, so it is test bench clock, that is 1 bit, and then we have input, which we have 3 input which are 1 bit, so it's clock, and then it is load, and it is reset. And then we have the other inputs that we're gonna have. The output is is of wire, so we can write here wire, and that is of 3-bit, and it is Q. So the first thing that we're gonna do now, we need to generate the clock signal. So when we explain here how we generate this clock, so what we need to do here is just to write always begin and then end this. So this one always begin, it will run until the simulation stop. So I'm gonna create a clock signal of 4 nanosecond period. So half of signal is 2 nanosecond. So the clock is gonna be equal to 1 bit high bit at the first half of the clock signal, and the next clock signal, half of it is going to be 0. So each time is going to toggle from between 1 and 0, so it's going to be a clock with a period of 4 nanoseconds. So the next thing that we're going to do is to declare the inputs. So because now we're going to generate the input signals, the value. If you remember, in our explanation we just took random numbers, so we're going to generate random numbers of D. So what we're going to do here now is create another initial begin, and then end. So inside this initial begin, we're going to have a for loop. So when E is equal to 0, E is less than, so we're going to create like 20 random inputs, and then E is equal to E plus 1, and then begin, end. So inside here, we're going to generate a random value of input D each clock signal. So each clock signal, we're going to generate input. So at pause edge, at positive edge of the clock, we need to generate random signals. So the first signal we want to generate random, it is the test bench D, which is the input value of our register, and we're going to set to equal to random. So this is going to be a random number of 3 bits. It's going to generate, and then the next thing that we need to generate random is the load, because if you remember how we explain here, we're going to have a load controller when the register is active. So the register will be active when the load is high, positive edge, and the clock. Even here, you can see that only when the load is high, we're going to take the value in the register. So here we need to generate also but now it is of the load. But now this one is random of just 1 bit, either high or low. So now we have generated those inputs of the load and the D value. Next, we're going to generate the value of reset. So when we're going to reset our register. So now we need to create another initial begin. And then end. And then here, as we did previously, here at the first clock signal, so at the first positive edge of the clock, what we want to do at the first positive edge of the clock, we want to set the reset value. So to be of 1 bit. So we need to set here, we need to initialize our register to be 0 at the first clock signal. And then we're going to create another for loop. Now is j is equal to 0, j is less than. For example, here now we're going to generate this 8 times, and then j is equal to j plus 1, and then begin, end. So what we're going to do now here is to make sure that our clock for the reset, it is not high for the rest of simulation. For example, these first 8 clock signals, we want the reset value to be 0. So what we're going to do here, just copy this one and paste it here, and we want for the 8 clock pulses, so the first clock pulse is 1, but the next 8 clock pulses, it is 0. And then what we're gonna do now here is for example, we need to make sure if we have our reset here, for example, it's high, and then we have low, so we can take those values, and then we can test other scenario if they are high, if we can reset our values, and then we can set it to 0 again. So in the next 2 clock, after 8 clock, we want to asset the reset to be 1, and to see if our register, it will be 0. And then what we can do now for so this one, it is the first clock, it is high, the next 8 clock, it is 0, and then the following 2 clocks, so that is 11 clock, it is for clock 10 and 11, it is 1, and then for the rest of the clock, we want it to be 0, so we need to create another for loop. So for example 10 until the end of the simulation. Begin, end. So here we want to be 0. Now what we can do next is to declare our integer for the for loops. So we can just come here, integer, and then it's E and J for our for loops. And then what we can do next, we need to test the cases if our register take the values. So what we can do now is to create another always, but now we need to check it at for example, when we do test, we're gonna check it at negative edge of the clock. So begin, and then end. So here we're gonna do our test. So we're gonna determine the expected value of the Q. What we're gonna do now, for example, we're gonna test if the reset is equal to 1. So if we reset our register, we can say the next value of Q, it should be 0. So it is 3 bits which are 0. And then, for example, else if load is on, we can set like the next Q value is equal to the value of the input value of the register. And then else, we can just say the next value of the register, it's equal to the input of the register. And then, for example, here outside of the here we need to test, for example, we can just do that the current value is equal to the value of the register. But here we need to set this value each time when the clock is positive edge. And then we can do that test now to check if the value of the register is not equal to the current value. Then, for example, we can just display for example failed register. For example, value that we expect does not match expected. So the register value, it is this one, and the current value is this one. And then we need to declare those values, and all of this value are reg, all of them. So we have the next queue, and then we have current queue, and then what we need to do, because we can see here our for loop here is 20, so and then 20 clocks, and then we are using another clock here, so and then times 4 nanosecond, that is our period. So our simulation time, so let's just write, for example, initial begin, end, and then the simulation time, so let's say 110 second, and then this is our simulation time, finish, the end of the simulation time. So let us save this and try to analyze and synthesize to see if there is something wrong here, and then we can fix it. We see that we have some errors, so let us see those errors here. Say line 65, 75, 86, 95, okay. 65, we can look at the error 65, we can see that we don't have a semicolon here, and then 75, yeah, we are missing the at sign, and then we can see line 86 here, 86, there is no, and then 95, let's see 95, we can see that is the end module. Okay, let's see, okay, we can see that this module shouldn't be here, and then we need to give our module name here, for example module 1. So Let's save it and try to analyze and synthesize again. Yeah. So on the next video, we will simulate this one and analyze the result.